Hi everyone, my name is Duco Pulle. I'm the professor at the RIT High here, and we're seeing also chief engineer from electrical drive engineer from Altair Embed. We have written a series of books, and much of what I'm about to show you today is based on what you see in the book. Our second edition of the book with my colleague Prof. Duco will appear in the second half of the year, which is the second edition of Applied Control Electrical Drives. That controls any type of drive, including also with Embed. So today we're going to use Embed and show you position control of a PM synchronous, which is the machine you're seeing down there. It is tied in this case to the TI unit 0049 with a Cavani inverter board, and we measure always in any board we do in our books 7 measurements, 3 currents, 3 voltages, which is the phase voltages, low pass filtered, and the DC bus. So 7 measurements is always critical. The machine is a machine. We do not refer to a machine as a plant in any of our books. If you refer to it as a plant, you should be taking up gardening. Machine is something else, and that is what we refer to here. Now, in Embed in this case here, we are looking at the going to see position control using Embed. So here we see the first page, which is this blue module here, which needs to be compiled. That is connected in this case, we connect to a 0049 processor and through an interface, a JTAG, which is the one on here. Nothing else required. If we click into it, and again, the details are in our books, you see here the main motor control. This is a fixed point. This is one of the few and the best fixed point environment you have with embedded control. There is nothing like it. And that means your operational variables have to be defined, full scale, and the converter variables. Right. The main motor control in this case is triggered at 10 kilohertz every sample. And we have a speed controller. We have an angle input, encoder input, which gives you the angle because we have a encoder connected to the unit. We have the ADC unit here, which collects the 7 measurements, and the alpha beta currents and voltages are converted into 4 signals and the DC bus voltage, and they are fed here. For example, the voltages are measured here and are fed to an input power because we measure input power. Right, the FSC speed controller. If we click onto that, you see a standard synchronous current controller. Inputs are the alpha beta measured currents, the ID, IQ references. The DC bus voltage is inverted and also fed into it. And output is the modulation index, and that is used by the PWM units. The Q reference, the quality current, is what is important in this case, and it comes if we have speed control through the speed controller. And if we have position control, then the speed control reference is provided by the position controller. It provides the angle, and a slider is connected to the reference, as we will see shortly. The whole process of running this is very easy. All we have to do basically is select this module as is, and simply go to Tools, go to CodeGen, and compile and download. Nothing else. I've done that, and now we move on to the next file, which is the run file, which is what I'm about to show you. If you run this, first put power on there, and the first thing to do here is check that you have the correct file. That is the file we are using today, and this is the whole unit. What you see here are the sliders for speed, angle, position, ID, IQ, KP, KI for speed control, an encoder offset, which is critical, and KP and KI for position control. The graph here shows you the per unit current or the per unit measured voltage. Now also shown torque, speed, input power, because we measure voltage and current, and DC supply, which is nothing else, input power divided by the bus voltage. Now, in running this thing here, we certainly be sure it's off. We have FOC on, and we have, in this case, speed control on, position control is off. So if we download the file, the first thing we see is, check on it, is the DC bus voltage. It's 24 volts, it's moving. You also see the CPU which is the percentage time per sample for 10 kilohertz, is only 7%. This is due to the fact that we are using fixed point environment. Right, to start this unit, we have now, for example, the shaft. We've got this little banana plug on there to show you position. But let's do first speed control. And the speed control, I'll set that very low and turn it on. And we see here, when it turns on, it's turning. And we see here at 80 RPM or 60 RPM, we can adjust that. Now at 60 means a rotation, 1 rotation per second. Now, the thing we see here, which is really important, is the blue vector is the voltage and the red is current. So as we increase the speed, the EMF, because it's mostly reduced by EMF, has to be at 90 degrees to the D-axis, which is the green vector. So now if we load the machine, the green vector increases. You see that? This is the instantaneous current also. But as we load it, and we see torque increase, speed stays the same, and input power, which is offset scale. But it's really interesting. Now look at this for the encoder offset. If we run the machine, for example, a little faster, EMF increases. Now the encoder offset is really the EMF has to be vertical to the D-axis, and by moving the encoder offset, you can see here that we can shift it, and it needs to be aligned perfectly. If we go negative speed, it will be exactly there, and again we can align it. So there we see it, and if we load the machine, then we see basically then the EMF should come slightly to the left, in the second quadrant. So try again. Here we see it, and we can move it up a little bit. That's about the best for it. Loading it, you see it, and if you reverse it, and reversing it, bang it, it'll come down there. So that's exactly what we see. We see a lot of information. Many others, is it blind? Because we measure voltages and currents. Now, the only thing we now do is speed control. Speed control. If we add, for example, a D-axis negative current, there you see it. You'll see it on the negative axis. And of course your voltage will also change. Positive current, there you see it. It doesn't affect the torque, of course. In this case, we're running no load. Adding a torque component will, of course, give you a Q and a D component. There's no field weakening for this machine because the short circuit current is very high. Now, reducing the speed, if we move to position control, which is now here, we now have position control. Now the theta reference is now at 0. This is your 0 reference. And if we start to move it, you can see perfectly, we see control. If we were to move it by hand, the torque, the current vector will also happen. As you can see here, the red vector, because you are applying torque. And it's exactly what you see here. So by rotating it, we can move it around as we speak, and we can set up the dynamics by, for example, putting a step current wave in here. A voltage pole, a square wave, and you can simply move it around and optimize the KP, KI, and even a differential, derivative. So there you see, in summary, what can be achieved with this type of setup, and how easy it is to move from compiling and back into controlling it. And the point is, you can be creative with control, with Embed. And that is what we're showing here as a first example, and to see how powerful this environment is. Thank you for your attention.